There's a public perception that a science related to rocketry is very difficult. Hence, the negative expression is not rocket science, which is said about almost anything that is not difficult. The truth is that the physical and mathematical foundations of rockets are not really difficult, which we'll attempt to show. What is difficult is not rocket science, but rocket engineering. The basic principles underlying rocket science were laid down by Isaac Newton. However, applying those principles to escape the Earth's gravity requires high pressures, temperatures, and velocities. And finding materials and building structures to withstand these parameters is the really difficult part. And so, presented for your consideration, the rocket equation, a mathematical equation that describes the motion of vehicles that follow the basic principle of a rocket. The equation is named after this guy, and it's always a guy. His name is Konstantin Tsiolkovsky, a Russian scientist who independently derived it and published it in his 1903 work. While the derivation of the rocket equation is a straightforward calculus exercise, Tsiolkovsky is honored as being the first to apply it to the question of whether rockets could achieve speeds necessary for space travel. And did I mention that the relation F is equal to ma for high school physics class is applicable for the motion of a rocket? Oh yes, bet you didn't see that one coming. As somewhat of a spoiler, F is equal to ma is totally inadequate in rocketry. Many high school students learn that Newton's second law may be written as the formula F is equal to ma, where F is the external force on the body, m is its mass, and a is its acceleration. If we apply this formula to rocketry where the external force is 0, at least in deep space, we'd have to conclude that the acceleration of the rocket was 0. That is, a rocket could never work. However, this is obviously not so. One other reason that in rocketry F is equal to ma doesn't really work is due to the fact that the mass of the rocket is continually changing as the propellant and oxidizers are shot at the back of the rocket. Let's use this beautiful rocket as a case study. Let's give it a name. Well, I'll call it Gemini. Gemini as in constellations. So we want to move Gemini from Earth's orbit at about 8.8 kilometers per second to Mars and stay in its orbit. The question you are battling with is, what type of rocket should you use? By how much change in velocity do you need to move to Mars? Since the external force in deep space is 0, we need a force that will move the rocket. This force is provided by the thrust from the exhaust of the rocket and is calculated by multiplying the exhaust velocity by a small change in mass. This is what is known as a thrust equation. But why a change in mass? Well, as you can see, the mass is not constant but continually reduces as the fuel is shot out the back of the rocket. And since for every action there is an equal and opposite reaction, the force that moves the rocket becomes the same as that of the thrust. Hence the equation F is equal to ma is equal to m times dv dt is equal to negative of the exhaust velocity times the m dt, where dv dt equals acceleration, that's differentiating the velocity. So making dv the subject, we have dv is equal to negative of the exhaust velocity times dm over m. Now by integrating this equation, we get the final velocity minus the initial velocity, which results to the negative of the exhaust velocity times the final mass over the initial mass. And to make this equation work, we need to multiply it by the natural log. If this seems like rocket science to you, which it literally is, well, don't worry. The key takeaway here is that in a chemical rocket, the propellant burn, producing hot gases which issue from a nozzle at one end of the tube. The ejection of these gases creates, under Newton's third law of motion, a reaction force upon the rocket, causing it to accelerate. How much acceleration do we get by burning all the propellant in the rocket? Well, that's given by the rocket equation, which Konstantin Tsiolkovsky applied in the late 19th century in his investigation of the feasibility of spaceflight. For his ideas, careful research, and great vision, do you also believe Tsiolkovsky to be the father of modern astronautics? Well, let me know in the comment section. Be sure to subscribe. Thanks for watching. Peace.